Welcome back. We're going to take a look at collisions and the coefficient of restitution. The derivation, you might say, of what is the coefficient of restitution, and if we know that, how we can solve certain problems, or if we know certain other data, how we can find the coefficient of restitution. Okay, so this is at the level of maybe a sophomore mechanical engineering, or like a sophomore class in mechanics for physics majors at a U.S. college or university. Okay, so I'm assuming that you already know a little bit about conservation of momentum. Okay, but if not, you'll probably learn something if you keep watching. Okay, so before a collision, let's suppose everything's happening along a common line in one dimension. Before a collision, let's suppose we have object A with velocity v sub a approaching object B with velocity v sub b. Maybe both are moving to the right. Okay, if B is moving to the left, we'll just use a negative value for its velocity. Okay, now during the collision, several things are going on. And then I'll get to that in a minute. After the collision, things are continuing to move along this common line, but each object has a new velocity. Okay, v sub a prime, v sub b prime. Okay, so what's going on during the collision that we need to know about, or could be interesting? Okay. Well, there are two different phases, we say, during the collision when these objects are in contact. We call those the deformation phase and the restitution phase. Okay, so during the deformation phase, these two objects exert forces on each other. We might call these the deformation forces. Okay, F sub d, which A exerts on B. And then by Newton's third law, the force that B exerts on A is negative F sub d. Okay, equal opposite forces. Okay, now this force could vary with time during this phase of the collision. What we are really interested in is something called the impulse. Okay, which is the integration of force over that time of contact. Okay, so we can talk about the deformation impulse, and then later we'll talk about the restitution impulse. Restitution force, restitution impulse. Okay. Now, when you have maximum deformation between these objects, okay, both will undergo just a slight bit of deformation, even if they look, completely rigid, completely solid. Okay, so at this maximum deformation, both objects will be moving at the same velocity, which I will call v. No subscripting, no priming, so forth. Okay, then they start kind of regaining their previous shapes, and this phase is called the restitution phase. Okay, they still exert forces on each other, but they may not be equal to the forces during the deformation phase. So we call these the restitution forces, but more importantly, we need the restitution impulse. Okay. All right, so there's our setup. All right, now what I'm going to do is scroll down the screen here. Excuse me. Okay. All right, now what I'm going to do is use something called the impulse momentum theorem. Okay, and if this expression is too mathy sounding, Sometimes I like to call it the impulse momentum principle. Okay, and what it says is that the impulse acting on some object or system equals that object or system's change in momentum. Okay, where momentum is equal to mass times velocity. Okay. All right, so let's apply this impulse momentum principle to each object from the deformation phase and from the restitution phase. Okay. All right, so for the deformation phase, object A, okay, we're using this impulse momentum principle. Okay, the impulse it receives is negative I sub d. Okay, negative because it really receives it from object B, which exerts a force negative F sub d. So when we integrate that, we get negative I sub d. This is going to be the final momentum of object A minus its initial momentum before and after that deformation phase. Okay, so at the end of the deformation phase, both objects have this common velocity v. And then prior to the deformation phase, object A had a velocity v sub A. Okay, let's do the same thing for object B. Okay, so in this case, positive I sub d, this is going to equal m sub b times v minus m sub b v sub b. Okay. All right, now let's do the same thing for the restitution phase. Okay, for object A, it receives impulse negative I sub r. Its final momentum is going to be m sub a v sub a prime minus its momentum at the beginning of the restitution phase, m sub a v. Okay, in other words, that common velocity v. Likewise, for object B, I sub r, m sub b v sub b prime minus m sub b v. Okay. All right. Now, a couple things happen here, and some of it is a little anticlimactic. But basically, this is how we arrive at conservation of momentum. If we take the sum of the two impulse equations during the deformation phase, well, the impulses cancel out, basically because of Newton's third law. And what we get, I'll just kind of simplify things in combining a couple of steps. Okay, at the end of this deformation phase, both objects have a common velocity, so we can factor the masses, or sorry, factor the velocity out. So we have the sum of the masses times v, and that equals m sub a v sub a plus m sub b v sub b. So this is basically conservation of momentum before and after the deformation phase. We can do the same thing for the restitution phase, and what we find here is m sub a v sub a prime plus m sub b v sub b prime equals the sum of the masses m sub a plus m sub b times v. Okay, and again, this is the left-hand side. That's the momentum of the system after the restitution phase, and then the right-hand side before the restitution phase, when they have the common velocity. Okay, now what I can do is I can combine these. Okay, you'll notice here that these two members of those equations are equal, and what I can just eliminate each side of those equations, equating the remaining two. And we get basically conservation of momentum for the entire collision. Okay, so like I said at the beginning, if you know a little something about conservation of momentum, this is not really that surprising. Okay, but it forms one of the ingredients for the final scheme. And some of the things we did to set this up with the impulses, for instance, it will be helpful in a few minutes. Okay. All right, so let me scroll the screen here again. Excuse me. All right. Okay, now we're going to move into talking about this coefficient of restitution. Okay, we define this as E, and we define this as the fraction of ratio of the restitution impulse to the deformation impulse. Okay. So basically, here's what it means. If the restitution phase does the same thing as the deformation phase, just in the opposite time sequence, then this coefficient of restitution will be equal to 1. And that results in what we call a perfectly elastic collision, in which all the kinetic energy is conserved. Okay? Sometimes this isn't the case. The restitution does not go all the way back. There's some permanent deformation during the collision. Okay, and this coefficient of restitution is less than 1. Okay, then if the objects stick together and continue moving at a constant velocity, basically you stop the process that I've described above immediately after the deformation phase. And the objects continue moving at that constant velocity. There is no restitution impulse or restitution phase, and then E is equal to 0. Depending upon what level you're learning at, sometimes we call this a totally inelastic collision. Okay, that seems to be common in introductory physics, or in the next level, say mechanical engineering, when E is equal to 0. Sometimes we call this a plastic impact. Okay. All the same, this is our definition E of the coefficient of restitution. Now, we can get two different equations for E. Okay, depending upon which version of I sub R or I sub D we are interested in. Okay, so E equals, all right, now if we think about this in terms of object A, okay, the restitution impulse for object A from up above, you need to kind of go back to earlier in the video to take a look at where I'm getting this from. That's M sub A V sub A prime minus M sub A V sub A. I beg your pardon, that's just M sub A times V. And then divided by the deformation impulse, M sub A V minus M sub A V sub A. Okay. Now what we're finding here is that all the factors of M sub A are going to factor out and cancel. So we get this expression. Now we can do the same thing for B. Okay, once again, I'm borrowing from an earlier formula. So the restitution impulse, M sub B V sub B prime minus M sub B V over M sub B V minus M sub B V sub B. Okay, as before, the masses will factor out and cancel, and I get V sub B prime minus V over V minus V sub B. Okay, well, these should be equal to each other, since they both came from our definition of E. All right, so what we can do is we can basically eliminate that common velocity v that the particles had in between the deformation and the restitution phases. Okay, so with some details here, what we'll do, each one of these is equal to E. Okay, so let me take each one and cross multiply, you might say, just to get rid of any fractions. Okay, for particle A, that's going to be v sub a prime minus v equals ev minus ev sub a. Okay, what I'll do is I'll just do parallel steps with this other formula. Basically, I'm just replacing the a subscripts with b subscripts. So v sub b prime minus v equals ev minus e times v sub b. Okay, what I'm going to do with these two equations is I'm going to try to eliminate the v variable. So let's get just the plain v variable on the same side of each equation. Okay, so for the particle A, I'm going to write v sub a prime plus e times v sub a, and that will equal ev plus v. Okay, particle B equation, it's going to be the same, look pretty much the same, except I'm just changing the variables, sorry, the subscripts, a to b. Okay, so what I have now is I have ev plus v equaling two different things. So the wavy underlines I'm going to set equal to each other. Okay, so what I'm going to get here is v sub a prime plus e v sub a equaling v b prime plus e v sub b. Okay. All right, so I'm just going to shortcut the rest of this and then solve for e. And when we do that, we get fraction for e, v sub b prime minus v sub a prime over v sub a minus v sub b. All right. Now we can identify a couple of interpretations for these numerator and denominator. Okay, for the numerator, this is the relative velocity of the two particles after the collision. Okay, now if you think of A as kind of like an incoming or projectile particle, B as a target particle, possibly an outgoing particle. Okay, after the collision with the primes, you can think of it as the target moving faster than the projectile, which might be true, very commonly the case. And then before the collision, this is the relative velocity before the collision in the denominator. Now in this case it's a minus b because the projectile is probably moving faster than the target previous to the collision. All right. Now finally, let me put one more thing on here for us. Let me just remind us about conservation of momentum. Okay, m sub a v sub a plus m sub b v sub b equals m sub a v sub a prime plus m sub b v sub b prime. So together, what we have here are essentially two equations in two unknowns that can be used to solve at least one-dimensional collision problems. Okay, the idea here is very often that v sub a and v sub b are known before the collision. V sub a prime and v sub b prime are not known after the collision. Okay, the trouble is if you're just looking at conservation of momentum, you've got two unknowns here, but just one equation. All right, well now we have a second equation in the same two variables, v sub b prime, v sub a prime. So if E is known, this permits us to solve for the final velocity of both objects. Or possibly you have the final velocities. You need to kind of work backwards, solve for the initial velocity. Maybe E is one of your unknowns. Okay, there are lots of different variations here. Okay, well, I hope this has been helpful. I'm planning more videos in the realms of introductory physics, mechanical engineering, maybe some pure math. Hope you have enjoyed. And thanks again for stopping by.